We're going to do something a little bit different this morning. We're actually going to look at some data. It's been a wonderful summit, and everything is the data revolution, and we heard a lot about data demands, and the next day, day two, data suppliers. And we haven't seen that much data, actually. So this morning, we're going to have a look at some new data. It's very special data. It's a global ecosystems data set. And we were asked to come and present this because it's extremely relevant to Eye on Earth, every dimension, as I'll describe shortly. I'm going to present an overview, and then a colleague of mine, Eric van Praag from Esri, is going to follow, and we'll attempt an actual look at the data, a demo, if you will. The internet has been a little bit slow for many of us, and so we'll just see how that goes. It's pretty early, so maybe there are enough people sleeping still that we'll have some luck with the demo. But there are so many names of Esri colleagues of mine that I haven't put up here, but there's a gentleman named Charlie Fry. He's the chief cartographer at Esri. He really has been instrumental in producing these data. And Randy Vaughn and Pete Aniello, and their new chief scientist, Don Wright. There's a whole team of people working on this from Esri. It's been a very interesting and working example, a model example probably, of a public-private partnership between the US Geological Survey, and I'm a senior scientist for ecosystems at USGS and Esri. And we're calling these things global ecological land units. Let me figure the technology out. I mentioned that there's great relevance for this resource in the context of Eye on Earth. And so I put up just many of the kind of Eye on Earth special initiatives. Eye on Biodiversity, I put that at the top because for me, the most important application for these ecosystems is for biodiversity conservation. I worked for 13 years at the Nature Conservancy before moving over to USGS. And as we all understand, biodiversity exists in three expressions, three levels: genetic, species and populations, and ecosystems. So ecosystems is one of the fundamental elements of biodiversity. And for conservation of global ecosystems, for representative conservation, we need to know what the ecosystems are that are out there on the landscape and where they are and how well protected they are, and figure out which ones we should be targeting for our conservation investments. So Eye on Biodiversity, certainly. Community sustainability and resiliency. Communities have a direct interaction with the ecosystems near those communities. Many communities derive their basic resources from ecosystems. Disaster management. We all know the mangrove story, that mangroves and coastal vegetation provide such an important buffer from coastal surges. So it's really important when we're thinking about disaster management and disaster management planning that we take into account the natural ecosystems there for their buffering abilities. Eye on Oceans and Blue Carbon. I'm showing you today the terrestrial ecosystems map, but we are already deep into the production of a global marine ecosystems map. And so that's coming soon. Eye on water security. We need water as human beings. It's one of the most important ecosystem goods and services provided, water provision from ecosystems. Again, I think we need to know where the ecosystems are that are giving us that ecosystem service, water, and what shape those ecosystems are in. Environmental education, this is also, for me, it's always been a teaching moment. There's a lot of different concepts out there for what ecosystems are, and you're going to hear one today. So for me, this is also a way to understand what we mean when we talk about ecosystems. And then ION access for all. The bottom line is that all these data are in the public domain, and even better, they are accessible as ArcGIS Online content. Working with Esri, they've just incorporated all these data into their content pool. And so it's really easy to get your hands on all these data, and I hope you will. Let's start off with the anchor publication, we call it. I brought a couple hundred, and I'm down to 5. I still have a couple. If you didn't get one, pick it up. We have an exhibit out in the hall, and we have this anchor publication, really beautiful piece of work, and for a deep technical document, which it is, I mean, you get all the gory details about how we conceive and construct these ecosystems. But it's also quite beautiful, lots of full color plates. We have a fold-out map of global ecosystems in the center. And this was actually, the print and the digital version were made available from the Association of American Geographers, and I thank them for that. They saw the value in having this resource in a glossy format as well as a big digital PDF. So I can get you the pub if you would like the pub. And what we found as well was that wasn't enough, and it's a scientific peer-reviewed publication, but a lot of people wanted a different kind of information. Where do I go to get it? How do I use it? You know, what are the data? What's the data construct? And so Esri has put together sort of a companion piece to this, which is an Esri white paper on the global ecological land units as an AGOL service. So this is a great one if you actually want to get your hands on the data through ArcGIS Online, figure out what it means in a data sense, and a number of great applications as examples of what you can do with these data. So we have the 2 publication resources. And just briefly, here in the beginning, and I'll get into this in some detail in a minute, how did we conceive of and map these terrestrial ecosystems? How do we define terrestrial ecosystems? What we did essentially is a classic GIS kind of stacked data analysis. We broke ecosystems down conceptually into their major structural elements, such as the bioclimates, the landforms, the lithology, and the land cover. And we mapped those surface features out globally, and then we combined those in a massive GIS union, which represents a stratification of the planet by climate, landform, lithology, and land cover. So in a nutshell, that's exactly how we map the ecosystems. And we have a total of 3,923 of these ecological land units that we have produced. Where did this all come from? I have a charge from GEO and GEOS. I'm the official task lead to produce a standardized, robust, and practical global ecosystem classification and map for terrestrial freshwater and marine environments. It's a very ambitious charge, and normally I would lose sleep over something as ambitious as that, but it's also my passion, and I have the great good fortune to be working on this probably for the rest of my professional life. And so it really is a wonderful thing to be doing, and many of my friends who know I'm crazy about ecosystem geography accuse me of inventing this language so that I could work on it later. And that's not the case, actually. The framers of the GEO Constitution, the pioneers of GEO, put this task together. And then they started emailing people around the world that might have some ideas on how you might do such a task. And so one day I got an email with this kind of language in it, and they said, we know that you've mapped some continental ecosystems, because I had at that point. And they said, would you have any advice on how you might undertake such an activity? And I gave them a lot of advice in that email. And the next email I got, which was probably a few hours later, was, congratulations, you're the task lead for this. Please, convince USGS to allow you to do this. And USGS obliged, and very thankfully, this is what I get to work on. So it's actually the case that GEO, it's an intergovernmental protocol, over 100 nations are signatory. It's not a binding protocol, but it's serious business, and it means the United States is responsible for this task. And the USGS is the designated federal agency, and I'm the guy in USGS as the official task lead for that. So that is the commission. It's wonderful that I have this commission, because otherwise I would be doing this anyway, and people would say, you're building it hoping that they will come. And I can say, no, I'm doing this because I'm required. I have a charge from GEO to do this. So that's the origin of the work. The basic question, well, what good is it anyway? What do we need a global ecosystem map for? These are what I believe are the most important applications. I'm hoping that as the resource gets out there and gets used a lot, people will tell me that they're using the global ecosystem map for all manner of different applications, some of which I might not even be able to imagine at this point. But for me, the really important ones are assessing the economic and social value of the goods and services from ecosystems. That's really huge these days. Everyone is interested in economic and social valuation of ecosystem goods and services. And we feel that because the ecosystems are the very service provider units, that whole discipline really should start from an understanding of the ecosystems and their distributions that are providing those critical goods and services. Conservation planning, I mentioned. Your basic gap analysis is you map ecosystems, you overlay protected areas, and you immediately find out which ecosystems are represented in that protected area network. Unrepresented, poorly represented, well represented. And the ones that are and underrepresented might become a focus for your conservation attention. Analysis of climate change impacts to ecosystems. Everybody wants to know how is climate change affecting ecosystems. They ask the question, and my question is, well, what even are the ecosystems that we're talking about here that are being impacted? And so again, for impact studies, climate change and others, invasives, fire, land use, et cetera, it's really good to have your ecosystem distributions mapped out for you. Global environmental security, it is a fact that nations go to war over these ecosystem resources. So we believe that an understanding of where these ecosystems lay on the ground is important. And then you have your old-fashioned resource management. Some agencies have an ecosystem-based management mandate. And so whatever their jurisdiction is, they're required to adopt an ecosystem management focus. Well, they need to know the ecosystems that are in their jurisdictions. And then research, the scientific community is always interested in ecosystems. They are usually more interested in ecosystem function, and they like to get inside ecosystems, instrument them, figure out how they work, characterize the ecosystem processes that are occurring. That is ecosystem function research, but there's a whole other part of science, which is understanding ecosystem distributions. Ecogeography, it's called. It's like biogeography. ecogeography, the study of why ecosystems are, well, where they are and why they're there. So those are most of the applications. This will look to you like an Esri slide, because it is. And I love this slide. When they gave this to me, I thought, I'm going to use that, because it shows in a glance the primary audiences as well as the data architecture concept. And so our audiences are many. We sort of feel that the landscape ecologist will be the first to arrive at the resource and kick the tires. Resource managers, geodesigners, and then we put the public up there because we feel like this ought to be a resource that anybody can get their hands on and understand. And so we have a strategy from the beginning, which is try always to simplify things to the level of a sixth grade understanding. Because if a sixth grader understands it, then we're all going to understand it. It's as simple as that. So we have this kind of sixth grade thing going on with the data. All the data are they're in ArcGIS Online. It's a major resource, and actually that enables you to assess the data in the context of many, many other global data sets, which is one of the great things about having it living in ArcGIS Online. And then it isn't just the data. There are many tools. There's several apps. Eric is going to show you some of the apps. There are workflows. We have authoritative classifications. And this is produced by USGS, so it has that sort of official government data stamp on it. And yet we're going to update it. We're already on a version 2, actually. It's less than a year old, and we've improved the version 1 up to a version 2. We've launched it at several domestic in the U.S. Events, like the AAG annual meeting, the Ecological Society of America. They had their centennial meeting earlier at the Esri UC, and so we usually have this wonderful walk-up display. That was a bit much to bring here. I wanted to, but there wasn't really an opportunity to do that. But we are putting it out there, and we're showing this map of the sort of foundational partners. USGS and Esri have built it. AAG has published it for us, and GEO has commissioned it. GeoBond, the Biodiversity Observation Network, there's a task within the GeoBond agenda about this. And it's increasingly exposed. We launched it in December last year at the ACES, a Community on Ecosystem Services conference in Washington, D.C. And it was presented as part of the President's Climate Data Initiative on Ecosystem Vulnerability. And it was announced by Secretary of the Interior Sally Jewell at that ACES conference. So that was the launch moment, and then the media has gotten a hold of it, and so it's really easy to find now. If you just Google Global Ecological Land Units, you'll see all the blogs and the media stories and the Wired piece and everything. So it's out there. I like the kind of, like we're on a boat. And so that was a basic overview. I'm going to just take a few more minutes and get into the nature of the concept, how we define and map ecosystems, because there's so many ways to think about ecosystems. This is one I happen to have on my desk at work. It was a gift from my wife. You can buy these in a Brookstone store in just about any mall or airport. They were, I think they cost like $75. I always wanted to get one, but I thought that was an extravagant purchase, so I never did. And then she gave it to me for my birthday. It's a closed ecosystem. It has living organisms in their non-living context. I don't have to do anything at all except make sure that my office doesn't drop down and get too cold at night. That's the only maintenance required for my personal ecosystem. But I really am including it so you get the the feeling that there are so many ways that we can think about and define ecosystems. And here are some of the best ways that I've come across. This is just a wonderful graphic where I think the average human being, if they think about ecosystems at all, which might be a stretch, I don't know, but they would tell you, oh, ecosystems are living things in their non-living environment. Absolutely correct. And they have an understanding that, okay, it's the rocks and the climate and the living things there. So that's sort of like the average concept. And then this graphic on the right is one that was produced by Bob Bailey of the Forest Service. He showed an ecosystem as a vertical integration of these structural elements, the climate regime, the organisms, the landform, the water. And when I saw that map, I remember, being extremely impressed. Oh, now I get it. Now I see what an ecosystem is. But the next page, I think it was the graphic that changed my life, and some of us have those graphics. And this is a graphic that shows you that as some of those structural elements change across space, then so does the ecosystem. And I saw this and a light bulb went off, and I thought, that represents a methodology for mapping ecosystems such that if we map all of those structural elements out over space and vertically integrate them, then that could become a standardized way of conceiving of and mapping ecosystems. And so that's what we did, and it all boils down into this. I'm a minimum set thinker, so I always try to reduce it to the most ridiculous minimum set of important determinants. And for me, for terrestrial ecosystems, those are the landforms, the geology, the bioclimate, and the vegetation. The first three determine the physical environmental potential. The last one is a biotic response to that physical environment. And we map those out and we combine them, and globally, and we did all this at a 250-meter spatial resolution, pretty fine for the whole planet. We combined them all. We got what we call ecological facets. If you consider the Earth as a gem, and I certainly do, then these are the facets on that gem, the unique combinations of these four inputs. And we got 45,000 of those, way too many for me to say, oh, we mapped 45,000 ecosystems on Earth. It's an unmanageable number, and we needed to group those, and so we have grouped those into ELUs, ecological land units, of which there are almost 4,000. So that's the methodology, and just stepping you through it, here's the global bioclimate layer that we developed for this project, and it uses temperature and precip data from all the MET stations around the world, a 50-year historical average, and it's essentially just hot, cold, and wet-dry combinations. Ombrotypes and thermotypes, we call those. So that's the global climate distributions. We used a digital elevation model to map landforms of the planet into these very simple macro physiographic regions: mountains, hills, flat plains, rolling plains. So we have a new DEM-derived global landform map. And then, fortunately for me, a couple of German guys recently just put together a compendium effort of global lithology. It's called the GLIM, Global Lithology Map. And they went out and got all the lithology data and soils data and geology data and put it together into the first reasonable global lithology map. And I saw it, and I said, great, now I can map global ecosystem, because finally the lithology layer exists. And they've been wonderful to work with. And then for land cover, we're using the European Space Agency Global Land Cover product, because it has great classification resolution. Lots of these classes, not just forests, grasslands, wetlands, shrublands, but different classes of those. And we combined them all, and then we got those 45,000 ecosystem facets, and then we aggregated those up into the 4,000 ELUs. To me, this is a stunning image, and I find it stunning because it looks like a satellite image picture of the Earth, and yet it is a modeled representation of the Earth's ecosystem. It's a modeled picture. And just to show you what it looks like for some continents, there's North America, South America, and Africa. And to show you also that it's rich, its spatial resolution at 250 meters allows you to really zoom in. These are the Ethiopian plateaus, and you can tell from all the dendritic networks and the flat plateaus that it just looks right, and it is right when you go in and look at it. And it's also beautiful. This is one of those sort of earth as art kind of concepts. So you can zoom in, and in the Sierra Nevadas of California, there is a place that has, in the smallest area, the highest concentration of diversity of ecological land units. We call that ecophysiographic diversity, and that's Lake Tahoe and Mono Lake, and right there near the eastern slope of the Sierras, near a place called Bridgeport, California, is the highest, the most ecophysiographically diverse place on the planet. Who knew? It's called the Sweetwater Range, and I have yet to get there, although I backpack in the high Sierras all the time. But I've never gone over to that other side and I know it's true because you drive by and you see all these different geologies. You see browns and whites, and it's just an incredible place. And quickly, almost done here, Eric. Can we do this for marine? Can we map ecological marine units? Because I have to, that's part of the charge. And I have to map ecological freshwater units as well. The answer is yes. What we have to do is figure out what these analog concepts are. And certainly landforms, well, we have seafloor landforms like seamounts and submarine canyons. So that's an exact equivalent. And then the substrate matters in the ocean as well. And then what do we use for bioclimate, for climate? Well, that's sort of like temperature and salinity gradients and currents. And then the vegetation is the marine biota. So we just have to figure out what the right analogs are. And of course, we're working in 3 dimensions now in the ocean, so it's not a 2D pixel assessment. It's 3D voxels, volume pixels. So that'll be a technological challenge, but we're already starting this and looks promising. And what we already know, for example, is imagine any volume pixel in the ocean, and we can tell you if it's on the benthic or if it's in the water column or if it's on the surface. And then we can tell you in this distance from shore if it's on the shelf, the slope, the abyss, or the hadal. We've already mapped this out from data. Because the really great thing about all this ecosystem mapping is it's not interpretive like all these ecoregion maps that came before. These are data derived using best available data sets at the highest possible spatial resolution. So we're going to do a data-derived global ecological marine map. And this is the voxel concept. So we will attribute the existing marine physical environment data to all those voxel cells. Then we'll cluster those out into these volumetric polygon regions. That will be really exciting. And that's what I wanted to provide by way of an overview, and people usually want to see the data, and so we'll hope that at this point we can get in and have a look. We've made several apps, and we have the data up there as ArcGIS Online content, and I encourage you all to take a look, and I'll hand this over to my colleague Eric from Esri now. Thank you.
Well, good morning, everyone. I think we have a few minutes, so let me see if I can show you here. So I have 3 websites open. First, I wanted to mention, I'm up here because I was asked to present. This is a project I really, really like, but I was not involved at all. So Roger mentioned the real guys from Esri who actually did the work with him. So we have 3 apps, basically. We have something that in Esri we call story maps. So you can actually see the different data set that Roger was talking about. Let me see if I can. There was a bit of a confusion. Roger asked me to talk about the Sierra Nevada, which he showed, and I saw he meant the Sierra Nevada of Santa Marta, which is in Colombia, which is a really amazing ecosystem. So I'm going to show you that briefly. It's a bit of a funny ecosystem. You see it here. It's not part of a mountain range. It's one of the highest elevations from the sea. It goes up to 6,000 meters. So you can see it there is very diverse. It's in the Caribbean Sea. And so what you can do with this is you have a story map. You can see different stories here. And if you click on the map, you can actually see the different ecophysiographic units. So you see warm, wet mountains on pyroclastic grassland. So you're going from the bottom up. If you go up a little bit, then you see warm, wet mountains. You can go up even a little bit here, cool, wet mountains. And I think if you go up here, you actually see hot, wet hills. No, that's not the one. So they have actually ice, which being in the equator is quite amazing. So you can, go through the map, see some of those, and also Esri and Roger put together a story map looking at the most diverse sites on Earth. So this is the one Roger was mentioning, the Seawater Mountains in California. So if you scroll, you have like different stories of different sites. Umblar in Turkey. So I think there's 100 sites altogether you can look at. So I invite you to see it. It's quite amazing story map that was put together. So this is like for the non-technical users. If you're a bit more of a technical user, there is another app called Eco Explorer. So you can actually see the map. Let's click on the map here. So on the right, you can see the ecological units, and on the left, you can see actually the components of it. So if you want to see, for example, landforms, you can click on here. Let's see if it works. We had some issues the other day. Okay, so you can see, for example, floodplains in that area of Africa. Let's look at landforms, for example. So you can have, so you see non-consolidated sediment there. You can actually switch through the different components. Let's look at land cover. You can see, for example, bare earth, or you can see tree cover here. You can move around. So quite a nice way of seeing the data that was put together in a nice application. And there is a third way of seeing the data. Esri has something called ArcGIS Online. It's a huge repository of data sets. So I log into my ArcGIS Online subscription here, and I could go to Maps. I could say, well, let's switch again to Colombia, see if that works. So this is the same Sierra Nevada of Santa Marta I was showing you before. You can say, I want to add a data set. I want to browse the living atlas layer. So some of these land units are categorized as living atlas, part of a living atlas that Esri put together. There is thousands of data sets, so let me choose ecosystems here. You can see the last one is a world ecophysiographic map. I can say add layer to the map. As a layer, let's see if this works. And there it is. So you have the map. And again, you can browse through it, you can pan, you can zoom in. We could go to the real or the other Sierra Nevada in California. And I find interesting, the Sierra Nevada, because Roger was telling me that for many years he wanted actually to go to the Sierra Nevada of Santa Marta. But it's a hard place to get to because there are gorillas, and actually the gorillas, it seems, are stratified by ecosystems. So it's kind of a wonderful, strange story that you have there. So I guess, I don't know, Roger, if you want to add something to this, but a quick overview. So we have those apps. They are available at Esri. You can check them out. If you look for story maps on ecological units, you go to the Living Atlas of Esri, or you go to the Eco Explorer, put those keywords in Google, you will be able to find the data. So in a nutshell, that's what it is.
Thank you, Eric. It worked.
Yeah, it works. I'm glad.
And we have a few minutes before the plenary this morning, so if there are any questions, we're happy to take them, and we're here for the rest of the day. Anybody have a question? Yes, Jordan.
How did you happen to choose 250 meters as the spatial resolution for this? And did you find data sets already made at 250, or did you have to construct those?
Great question. Thanks for that wonderful prompt, because that was something I meant to mention. Sometimes your spatial resolution comes from one of your input data layers. And in our case, that was the global digital elevation model. The USGS put together a global DEM called the GM-TED, and it had a 250-meter native spatial resolution. And so that was the data set that we used to define that was our set of pixels, and that defined the sort of land-water interface as well. And then we reconciled the other data sets to that one. And for example, the land cover from the Maris satellite was a 300-meter native resolution. So we sampled that into our 250-meter pixel framework. So the DEM established the pixel frame, and then we reconciled everything to that. The global geology data set, the GLIM, that one has an unknown resolution because it being a compendium of different sources of data at different qualities and spatial resolutions. You put all that together and you don't really know what the overall spatial resolution was, but we nevertheless took it and then put it into our 250-meter framework. And that's something they teach you not ever to do in GIS 101, is take a coarser spatial resolution data set and resample it to a finer resolution just so it matches something else. They teach you that, and we understand why that is, because we don't want to assume a higher spatial resolution in the data than actually exists. But we're aware of that, and in the end, it's just something that you need to caveat and make sure people know that you're using best available data. And so that's what we did. So that's how we got to our spatial resolution. And then the other part of the question, were these data sets available? The global bioclimates data set was available, but we had to fix it for what we wanted to do. It had some issues. And so we fixed that one. The GLIM came along, and we had to work on that a little bit as well. The global land cover data we just got straight from European Space Agency, and then the land forms, we built that one ourselves with the DEM. Yes.
I have a very quick question on accuracy of the.
Yes.
How to validate?
Yeah.
Yes. For example, when we use the land cover,
Yes.
and I think the ecosystem mapping is from a combination of several parameters, and one thing we could focus on is the validation work on.
Yes.
How to make sure So accuracy is better than the
Yeah.
other methods, yes.
Yeah, that's another great question. Thank you very much. I'm getting some feedback. Of course, there is no reference standard that we can use to compare against. The truth is not out there. There is no reference standard, so we can't do a traditional accuracy assessment against a reference standard. So we do the next best thing, which is what everybody does, which is to compare your product with other people's products. And we use we use a land cover as one of our inputs, and it itself has a certain accuracy, which is something like 75 or 80%. And we have done some spot checks of the data, and in all those comparisons with what other people call it, or in what you're looking at in the image, we've been very pleased with the accuracy, but we're unable to say, in the end, it is 81% accurate. If we could, that would be wonderful, but we can't do that yet. And you know, people that have a statistical background, they usually want to hear 95% confident or better, and they don't understand that in typical land cover mapping, if you get accuracies of 70, 75, 80%, that's pretty good. And so we assume that our ecosystems are probably in that range of 70 to 80% accurate. A colleague at Esri actually proclaimed that they were 80% accurate for the United States. We did a subset, but we need to have a validation process. I think maybe that's the best answer to your question. And I don't really know how to do it, but all I keep hearing at a summit such as this is crowdsourcing is the answer in the future. And so I'd like to see if the World Bank might make a lot of money available for people everywhere on the planet to go to a place and just tick off landform, yeah, they got that. Climate, yeah, that's right. Lithology, I don't know, because I don't know what that is. I don't know if that's carbonate or not. But maybe take a picture and then send that in. And so the dream is that we could have like a crowdsourced field campaign validation. But right now we don't have any formal plans to do that. Anybody else? Yes.
For the ocean mapping, thank you very much. Thanks for the presentation. For the ocean mapping, you have stated you are able to detect the temperature and salinity. Could you figure out the thermocline and halocline, and also phenomena such as El Nino? Thank you.
We are going to do our best. There are two global marine physical environment data sets that exist. One is called the GMED. It's actually a geo product, a global marine environment database. And it is a 1 kilometer horizontal by 50-meter depth spatial resolution. And they've taken all the temperature and salinity data that they could get their hands on and done this spatial interpolation. And so we are going to use that as our source of marine physical environment data. And there's another one put out by the Marine Conservation Institute. And so we will use those data, and some of our colleagues are saying we might be able to actually map the thermocline. And so we don't want to just assume that this notion of, the 200-meter depth apparently is a really big thing in historical tradition of oceanography, that everything above is warmer and lighter and everything below is colder and nutrient poor. We don't want to assume that. We want to see if using the physical environment data, we can actually map those clines. So we'll see. I don't want to promise it because it hasn't been done before, but many of my colleagues are really excited about, let's see if we can map those gradients rather than impose some fixed zonation epipelagic, mesopelagic. We have one guy in the steering committee who just doesn't want to do that at all. He says those are just lines in a book and hundreds of years of those kind of graphics. He says let's abolish that notion and just map these gradients and see how they are. And so we're going to do our best. Yes.
I would like to know, if possible, through your map and data set, to understand the historical change in the vegetation, land use. Is it possible, on how long it can, for example, if it's possible, for how many years, if I want to trace the change in a specific area?
Yeah, another great question. I forgot to mention that 2 of our 4 input features are what we consider permanent, enduring features of the environment, and that is the landform and the lithology. Those are not expected to change, although we as humans do move mountains these days, so it's not entirely accurate, but those are permanent features, whereas the land cover is changing from land use all the time, and now climate is changing as well. So those 2 inputs are temporally variable, and so as we go forward, we can either wait 5 years and get a new land cover map and then remodel the ecosystem distributions at sort of a 5-year interval, or we can model into the future projected land cover, land use changes. And there's also a lot of progress in backcasting as well, because we have the global image archive at our disposal. So we might be able to go backwards in time with the land cover. I'm not sure about the climate, although if you take that 50 years of meteorological data and start chopping that up, I guess you could go backwards in time too. So we could, in theory, do that with some pretty serious modeling. And these are the kinds of things that we're hoping the community will say, well, if you're not going to do that, that's what I really want to do. Because we're sort of already busy moving on to map marine, and after that we're going to map global freshwater ecosystems. And so we're trying to expose and make the data available for other people to do that kind of research. So we would really appreciate if somebody wants to check the veracity of the data as well as its utility for future modeling or backcasting. But I think there's a lot you can do. We just don't have any plans right now to do it. Yes. Here it comes.
You said you're already developing the second version. So in which direction you're further developing the product in the future? And what are your aspirations?
The version 1 is what you saw. And we actually built that using the ESA Globe Cover 2009 data set. And they have since put out an improved global land cover product, which they just call Global Land Cover. And they've done it at 2010, 2005, and 2000 epochs. And so because they changed that input, and then we ourselves also found that we could improve our global landforms layer, because you're never happy with your product. You model it, and you say, oh, that's great, and then let's use it in the global ecosystem. Then you look at it again, you go, I think the flat plains, we didn't capture those gentle undulations in the flat plains, so let's tweak the algorithm and see if we can get better terrain map. And we did that, so we actually have a new world landforms layer, and we have the new global land cover layer. So since 2 of our 4 inputs changed, then we recombined them to produce the version 2 of the ecological land units. So we did a version 2 even before version 1 was 1 year old. And we just did that because we needed to do that. But if we have a planned set of versions, I think we should do it on sort of a 5-year return interval, because if you try to detect a lot of change in less than 5 years, it can be a lot of noise. But if you wait 5 years and you see change, it probably happened. So if we do this epochal ELUs into the future, it'll probably be at a 5-year interval. We just happen to make a version 2 right away. Does that answer your question? I believe it's time for the plenary. Let me see. We're late for the plenary. We're late for the plenary. I'm so sorry. Thank you again for coming. Thanks, Eric.